Today you are going to be working in small discussion groups, and what you will do is individually you will watch this video on Edpuzzle, then you'll discuss as a group, and then you will answer individually on the Edpuzzle and then keep going. I realize there will be a little bit of wait time because you won't all stop and start the Edpuzzle at the same time, but this has worked in the past, and it's a good way to kind of have private discussions rather than giant whole class discussions where only a few people participate. So this is the first day of a 2-day lesson where we're going to looking at something called the normal force. And I just want to remind you about what we have looked at so far. So on the first 2 days of class, we looked at this concept of equilibrium, and we observe objects, the sled, moving at moving at a constant velocity, either not moving, which is a constant velocity, or moving at some value of constant velocity. So it's not speeding up or slowing down. It's either at rest or moving at a constant velocity. And the other thing, someone, I think this was third period, noted that our object was only moving in a straight line in one dimension, and that is also characteristic of equilibrium. The condition that caused that was we had balanced forces. And one of the things that I tried to point out is on the solutions review is that forces can be balanced in one direction and unbalanced in the other. So we have this diagram of a plane up here where I look at the vertical directions and the lift and the weight, the same arrow. And so the lift is making the plane move up, the weight is pulling the plane down. Because these are balanced, it's not moving in the vertical direction, either up or down. It's just flying horizontal or level. But I also notice that the drag arrow is the same length as the thrust arrow. So thrust is what makes it go forward, drag is what slows it down. These are the same length, so these are also balanced. So I can look at these conditions and I can say that the plane is moving with constant velocity in both directions. In the vertical direction, the constant is actually equal to 0, and then in the horizontal direction, it's equal to some value. So I can contrast that with unbalanced forces. In the vertical direction, I notice that these are the same length, and so the plane is not moving in the vertical direction, and so it's just moving level. But when I look in the horizontal direction, the drag arrow is shorter than the thrust arrow, and so they're unbalanced in the horizontal direction, and so I know that the velocity is changing in the horizontal direction. Okay, so that was number 3. And then number 4 is the coordinate axes are oriented in the direction of motion of the object. So mostly we've been looking at situations like this, where the object is moving horizontally, but we could have a situation where an object is sliding down the ramp. In order to analyze the motion, we have to tilt the x-axis, or if appropriate, the y-axis. One of the axes has to be in the direction of motion. So here it's moving down the ramp. And then the other axis, of course, is perpendicular to that. So that's what we've looked at so far in terms of our concept of equilibrium. And then looking at the conditions that cause equilibrium, I've introduced 2 new ideas. One of them is a system schema, where we represent all of the interactions in a region of space. So this is an example of a system schema for this block, string, and table. It's used to create a free body diagram. And that's the second tool that I've introduced, is the free body diagram. And what the free body diagram does is it shows all of the forces interacting on a single object in the diagram. So if I were to look at the interesting one to look at, I know we always look at the block, but if I look at the block, I would draw a free body diagram. As I look at the diagram, I can see that there are 4 forces interacting with them. I don't even really need to understand what the forces are. I can just look at the labels and put those on. Force of gravity, I know, always goes straight down towards the center of the earth, and this is what we've been calling weight. I also have an upward force. This is the force normal. and I'm actually going to talk about that today. And then we've got the string going forward, so that's FT, and then they've said that we have force of friction backwards. I don't know how this block is moving, so I really can't put in any congruency marks, but I just wanted to show you how we go from a free body diagram, or from a system schema to a free body diagram. So in the lecture today, where I'm actually going to talk about this thing called a perpendicular force. I know in the schema, they call it a normal force, but it's actually what I've been calling the perpendicular force. So as I lecture, I really want your feedback on how you feel about what I'm teaching you. I want honest feedback on this. And the idea is that throughout our lives, we have had a wealth of experience with the physical world, which leads us to feel that some things make sense and others do not. And a statement makes sense when we understand it at an intuitive or a gut level. At times we are confident about an answer and it makes perfect sense. For example, if a large truck runs into a small car, most people are confident that the car will get damaged. It also makes sense to them that the car would be damaged. So they know it's going to happen and they feel confident about it. And so in that case, I would give it a pretty high rating because it makes a lot of sense. However, there are times when we know an answer is correct, so we have knowledge that it's correct, but it doesn't really make sense to us. For example, many people are confident that when a person throws a boomerang, it will come back, but it does not make sense to them that it should come back. Why does it come back? What makes sense is that the boomerang should just keep going in a straight line like a ball. So how would you mark the make sense scale in this case for the answer that the boomerang can return to the thrower? You would mark that lower, like maybe a 1 or a 2, unless you understand how boomerangs work or you really have a sense of how they work. So the scale asks you to rate how much sense each statement makes, not how confident you are about the truth of the statement. So please circle a number. I'm actually going to have you respond on Edpuzzle. So here is our first situation. A book is resting on a table, and the question is, does the table push up on the book? So before you answer the question on Edpuzzle, I want you to discuss this with your group, and you might take 5 or more minutes to discuss this with your group, and then you will answer. So I'm not going to tell you the answer to that question. I'm hoping that we get to the very end of the lesson, you will not only know what the right answer is, but it will make sense to you and you will feel confident in it. So we're going to look at a couple of bridging examples to try to really understand and make sense of what is happening with the table. So the first one is a spring rests on a table and someone pushes down on the spring and compresses it. I actually have a spring that looks exactly like this, and so I highly recommend that you borrow the spring from me and actually test it out for yourself. So the question is, does the spring push up on the hand? Again, I want you guys to talk about this for at least 5 minutes. You don't have to come to agreement, but you want to do a deep discussion. Okay, so does it push up on the hand, yes or no? All right, deep dive discussion. How is this situation like the book on the table, and how are the situations different? So I want you to discuss that, and then you will summarize for yourself kind of your response to that. All right, so bridging example 2. Now I have a book resting on a soft foam pad, and the pad is resting on a table. The pad is not just out in space with nothing supporting it. So foam is on the table, book is on the foam. Does the foam exert an upward force on the book? Again, discuss before you answer, but you should answer what you think is correct. Don't let the group bully you into giving an answer that you don't believe is true. Okay, now you're going to do a deep dive discussion. Is this case the same or different from the table case? And again, I want you guys to, spend a reasonable amount of time discussing and then summarize what you think is correct when you respond on Edpuzzle. Bridging example 3. Okay, so now we've got we've got these two supports, and this is a flexible board, like a piece of balsa wood. And if you actually want to see this, I have a demonstration set up at the front of the classroom, and I can show that to you. So a book is placed on top of the flexible board. Does the flexible board exert an upward force on the book? Discuss it as a group, and then put down what you think is correct. Deep dive discussion, again, spend time fully discussing this. This is really where you're going to learn, are the discussions that you have with your peers. Now, your peers may be dead wrong, but just hearing them say things that are dead wrong, it will all of a sudden click for you. Your peers may be right, your peers may be wrong, but engaging in the discussion is where your brain is really going to fit things together. So, is this case the same or different from the table case? Why? Discuss, then summarize what you think is correct. Okay, I know it looks like exactly the same. Question number 3, suppose the board is twice as thick. How do you think the situation will change and why? So again, we're talking about, does the board exert a force on the book, an upward force on the book? Discuss. Okay, and then the last thing I want you to discuss with this is at what thickness does the board become rigid? So we're going to go back to our original situation. A book rests on a table. Does the table push up on the book? So to help you understand this, I'm going to introduce something called the springy model of matter. And this builds on what you learned in chemistry. So the idea is that we have these nuclei that have protons and neutrons in the middle of them. And these are like solid billiard balls. And what connects the nuclei together are electron clouds, and these electron clouds are squishy. They can move far apart like you're pulling a spring, or they can compress together like you are compressing a spring. And so the idea is when you have like a book, pretend that this hand is the book. When you have your hand resting on a table is made of matter, and matter is connected or has these springy connections in it that you compress some of those springs. So the atoms on the very top of the table that you are touching actually move closer to the atoms below it, and you compress them. Now, the very, very positively charged nuclei, as well as the electrons, they don't want to be compressed together, and so they push back. And so all matter, or the hypothesis is that all matter is actually made of these hard nuclei attached by springs that can be stretched or compressed. So I will put a link to a video demonstration so that you can see there's a very nice demonstration that things that are super solid, like the example here is a block wall, are actually compressible. Okay, last time. Book is resting on a table. Does the table push up on the book? And again, I want you to put the answer that you actually believe is true. And then I want you to think about which of the learning activities was most helpful to you today. So the pushing on a spring, hand pushing on a spring example, book resting on foam, book on flexible board, the springy model, or the video of the pushing force with the laser. And then do the homework and turn it in, and tomorrow we will finish up with this idea.